You can't put your shoes on before your socks. You can't pour the coffee before you brew it. Almost everything we do has an order baked in. Some steps simply must come before others. So here's the question. Given a giant pile of tasks that depend on each other, how does a computer find an order that never breaks a single rule? The answer is one of the most useful algorithms you've never heard of, topological sort. It's quietly running every time your code compiles, your spreadsheet recalculates, or a package manager installs dependencies. Let's see how it works. This is Logic Lab, where computer science becomes something you can see. Today, topological sort, turning a tangle of dependencies into a clean, valid order. First, we draw the tasks as a graph. Each task is a node, and we draw an arrow from it to B whenever a must happen before B. Socks point to shoes. Brew points to pour. These arrows have direction. It's a directed graph. And crucially, it must have no cycles. If A waits on B and B waits on A, no order can ever satisfy both. You'd be stuck forever. A directed graph with no cycles has a name, a DAG, a directed acyclic graph. Topological sort works on exactly these. So what are we actually looking for? A topological ordering is a lineup of all the tasks where every arrow points forward left to right. If there's an arrow from A to B, then it appears somewhere before B in the line. Do that for every arrow at once. Notice there can be more than one valid order. As long as no arrow ever points backward, the lineup is correct. We just need to find one of them. Here's the cleanest way to do it, called Kahn's algorithm. For each task, count its in degree, the number of arrows pointing into it. That count is just how many prerequisites are still unfinished. Any task with in degree 0 has no unmet prerequisites, so it's ready to go right now. Pick one, output it, and remove it from the graph. Removing it deletes its outgoing arrows, which lowers the in degree of whatever depended on it. Some of those tasks now drop to in degree 0, they just became ready. Add them to the pool. Repeat. Take a ready task, output it, peel away its arrows, free up the next ones. Keep going until every task is placed. The order you printed is a valid topological sort. But what if you get stuck, tasks remain, yet none have in degree 0? That's not a bug. It means every leftover task is waiting on another leftover task. There's a cycle. And a cycle means no valid order exists, by definition. The algorithm detects the impossible for free. There's a second classic approach using depth-first search. Explore each task fully, and the moment you finish one, push it onto a stack. Reverse the stack at the end and you get a topological order too. Same idea, different bookkeeping. Why care? Build systems like make topologically sort your files so each one compiles only after the things it includes. Spreadsheets sort cell formulas so a cell is computed after the cells it references. It's the same trick every time. Package managers order installs so every library lands after its dependencies. Course planners sequence classes after their prerequisites. Task schedulers, data pipelines, even resolving symbols in a program. All of it is a DAG waiting to be sorted. Recap. Model tasks as a directed graph with no cycles, a DAG. A topological order is a lineup where every arrow points forward. Kahn's algorithm repeatedly outputs any task with no unmet prerequisites, then removes it. If you ever get stuck, there's a cycle and no order exists. We've now sorted graphs every which way. Next, we shift gears to the data structures that make all of this fast, starting with the one that finds anything instantly. That's the hash table next on Logic Lab. See you there.